All right, in section 4.2, we're going to review a little bit about acids and bases, and then kind of what's going to happen if we react acids and bases, and then a new concept of oxidation numbers when we are talking about reactions. So last year, remember, we talked about acids and bases, and all acids start with what? Hydrogen. And that's kind of the basic definition of our arrhenius acid, is they start with hydrogen. If we continue, there are multiple definitions of acids and bases. Remember last year we talked about arrhenius. We've talked about Bronsted-Lowry. Bronsted-Lowry defines acids as proton donors. Now, remember, we typically refer to Bronsted-Lowry just as an abbreviation as BL acids or bases. So Bronsted-Lowry acids are proton donors. Now, if we flip-flop, we can talk about, well, before we flip-flop, let's quickly review our 7 strong acids from 4.1. Remember, we have the 3 halogens, chlorine, bromine, and iodine. And then we have perchloric, or chloric and perchloric. And nitric and sulfuric are 7 strong acids. Remember, those 7 strong acids dissociate completely in solution and therefore are strong electrolytes because their ions are very present. So, acids start with H. Bases. Bases, remember, always end in OH. So if we have a basic definition of arrhenius bases, they increase the amount of OH in a solution. Again, Bronsted-Lowry defined them slightly differently, where Bronsted-Lowry acids were proton donors, Bronsted-Lowry bases are proton acceptors. Now remember as well, what are our strong bases? They are all the elements in group 1 plus all the elements in group 2 with the exception of magnesium and beryllium. So magnesium and beryllium are out. So just like it says on the board here, you have the alkali metals group 1, and then you have calcium, strontium, and barium, which is the rest of group 2 outside of beryllium and magnesium. Now, real quickly, when acids and bases react, what are your 2 products? Let's see if we can refresh this. What are our 2 products with an acid and when an acid and a base react? Your 2 products are a salt and a water. So we have salt and a water. Remember, salt is a chemical definition and is not table salt such as NaCl. It's essentially the combination of a metal and a halogen, or a metal and a polyatomic ion forms a salt. So in an acid-base reaction, the acid is donating a proton. So in this example, water is the acid. It's donating a proton. NH3 is the base because it is the acceptor. If we talk about neutralization reactions, we're going to take an acid and combine it with a base. Now it's very obvious to you that in this example the base is NaOH because it ends in NaOH. However, the acid's a little more complicated in this example because you get CH3COOH. The H is on the end. It's on the right side. We usually write it on the left side. You'll see this vary, but CH3COOH is acetic acid. All right, it's acetic acid. You'll see it written as this. You'll see it written in a couple different varieties. Don't let it attempt to confuse you, but it is a neutralization reaction. Our 2 products are our salt, and we have really, sodium should be out in front here. It should be Na. Sodium acetate is our salt, and then we have water as our liquid. Now remember, if you had to write a net ionic equation for this, you would not include water as one of your products because it's no longer, the ions of water are no longer dissolved. It is a liquid. There are not ions present in solution. Another example of a real basic neutralization reaction, you have HCl with NaOH. Hydrochloric acid with sodium hydroxide. Very simple neutralization reaction, acid and a base. Our salt is NaCl, and our water, obviously form water in the liquid form. And what happens is, if we do the net ionic equation for this, the only thing that's changing its state is water. Nothing else is changing. Everything else stays in the aqueous solution, so all our ions cancel except those that are focused on water, and we get hydrogen and OH to form H2O. Now there are a couple of exceptions when we have acids and bases react, or when acids react with solids. And those two examples are what we call gas-forming products. And our two culprits are carbonate, CO3, and sulfite, SO3. And they both like to form gases. Carbonate likes to form carbon dioxide, and sulfite likes to form sulfur dioxide. So those are the two exceptions to this rule. So if you look at the bottom example here, we have calcium carbonate reacting with hydrochloric acid. You're going to get the salt. You are going to get a salt. Calcium chloride is a salt, and water, but you can see your third product is carbon dioxide. So carbonates act slightly differently than other reactants when we were talking about acid-base reactions. Below here is another example with sodium bicarbonate. So bicarbonate can also produce carbon dioxide. And if we look at a second example with sulfite, so we have strontium sulfite. When that reacts with an acid such as hydroiodic acid, HI, we get sulfur dioxide. We still get the salt. Our salt is strontium iodide, and we get water, but our third product ends up being sulfur dioxide as a gas. So there are a couple exceptions when we talk about gas-forming compounds. So here's another example of a gas-forming compound, except this time we're forming H2S as our gas, which forms as a gas. You could play this off as a double replacement reaction here. You have Na combining with SO4, you have H combining with S. H and S, when they combine, form a gas naturally. So yeah, I have to laugh at this reaction because it says you can carry out this reaction, but you might carry it out in the hood. H2S is going to smell like rotten eggs. It's going to smell incredibly disgusting in your lab if you didn't carry that out in the hood. So just a heads up there. One last thing that we're going to cover in 4.2 is we're going to talk about oxidation reactions. This is something new that we did not talk about last year. So if we look at oxidation reactions, an oxidation reaction occurs when an atom or ion loses electrons. So the O, all right, I've heard many ways to do this. I've come up with a mnemonic device. I just kind of go the O is in lose. So you kind of remember that the O is right away. So oxidation loses, reduction gains. And these are most commonly referred to as ox-redox or redox reactions. You have the reduction for or the RED for reduction, and the ox for oxidation, so they're redox reactions. But one can't happen with the other. So if something loses electrons, the other one has to gain. So that's why they're called redox reactions or ox-redox. So when we do ox-redox reactions, we have to work on assigning oxidation numbers to atoms. And this is kind of assigning the numbers, which is going to tell us whether or not they're losing electrons or gaining electrons. So when we come up with an oxidation reaction, we need to figure out what's losing and what's gaining. We need to look at the individual elements to kind of figure out their oxidation numbers. Well, there are rules to oxidation numbers. So if we look at oxidation numbers, elements in their elemental form have an oxidation number of 0. So if I ask you what's the oxidation number of sulfur, it's in its elemental form, 0. If I ask you what's the oxidation number of chlorine, well, that's a bad, I don't want to do that. If I ask you by itself in its elemental form, sodium is a solid. All right. It's in its elemental form, so it's 0. the oxidation charge of monatomic ions is the same as its charge. So if we look at not as a state, so if we do chlorine not in its elemental state as Cl2 as a gas, if it was Cl2 as a gas, it's in its elemental state, it would be 0. However, Cl has a charge, the ion has a charge of -1. So in this example, chlorine is going to have a charge of -1 because it's not an elemental state. So if we did NaCl together, Cl we know has a charge of -1 as a compound, sodium has a charge of +1 as a compound. So its oxidation numbers for sodium are +1, oxidation numbers here for chlorine is -1. Couple more specific rules. Nonmetals tend to have negative oxidation numbers, although it is positive that they can, or although it is possible, I shouldn't say positive, it's possible that they sometimes have positives in certain compounds. Special rule about oxygen. Oxygen has an oxidation number of -2, except in peroxide, in which it has an oxidation number of -1, and in peroxide peroxide is H2O2 if you don't already know that. So just a little heads up there, oxygen has an oxidation number of -2, except when it's in peroxide. That's the one exception. Another specific rule is hydrogen is -1 when it's bonded to a metal, +1 when it's bonded to a nonmetal. So hydrogen's kind of finicky, it can go one way or another, so it's -1 when bonded to a metal, +1 when it's bonded to a nonmetal. A couple other examples here. Again, most nonmetals are negative. Fluorine always has an oxidation number of -1. The other halogens have an oxidation number of -1 when they are negative. They can have positive oxidation numbers, particularly in oxyacids, or when they're an oxy ion. So when they're attached to oxygen, it's possible that they have a positive number. For example, here's a rare example, OF2, the compound OF2. One of the specific rules was that one of the specific rules on the last side is fluorine always has a charge of -1. Well, if there's two of them, I have a net charge of -2. Shoot. Bad example. Totally ignore that example. We'll come back to that in class. That's a poor example that I don't want to go over yet. So, fluorine always has a charge of -1. All the others have a charge of -1 except when they are oxyanions charged to oxygen. We'll talk about that OF2 example in a second here, or in class. So the sum of oxidation numbers in a neutral compound is 0. If it is not a neutral compound, the sum of oxidation numbers is just equal to the charge. So if, like, for example, we do an example like this. Let's go H2O. Well, remember what was the example when hydrogen is bonded to a nonmetal? Hydrogen is +1. In this example, I have 2 hydrogens, so it's +2, which means that oxygen is -2, which follows the rules. The charge here is 0 because I have a compound, and the charge is 0. If I take another example, like SO4 -2. All right, SO4 -2. We know that oxygen has a charge of -2. There are 4 of them. So oxygen is -8. Sulfur then has to be +6. The overall charge of this compound is -2, so the overall charge of my oxidation numbers has to be -2. Let's look at a couple more examples here. Let's take this one, Na2SO3. Let's look at our rules here. Na2SO3. Our rules state that oxygen is -2. We have 3 of them, so we have -6. Next up, sodium pretty much takes on its charge as an ion. Well, sodium has a charge of +1. There are 2 ions here, so sodium is going to have a charge of +2. And to cancel this out, because this whole compound has a charge of 0, the sulfur is going to have an oxidation of +4. Let's look at another example. Let's look at SCl2. SCl2. All the halogens have -1 outside of a couple examples. Well, if the halogens are -1, chlorine is a halogen. There are 2 of them. So chlorine is going to be -2. And in this example, sulfur would be +2. So you can see that not every number is going to be the same for each element, as sulfur has varied in this example. So, following these rules, there will be a couple examples on the quiz. There'll be a couple examples on the quiz on kind of how it works. But other than that, that is oxidation numbers, and that is the end of section 4.2.